So here I have a rubber stopper, and this rubber stopper is attached to a piece of fishing line. And if I take this rubber stopper, I can make it move around in a circle. I can swing it around sort of like this. And when I do this, my students in my normal classes often get very concerned because they're afraid that I'm going to lose my grip.
Well, aloha, everyone. Today, we're going to talk about centripetal acceleration and force.
Newton's first law says that objects in motion will stay in motion, and they will move in a straight line. So in order for something to move in a circle like this, you're going to need to have an external force acting on that object. In this case, it's this piece of fishing line that keeps it moving in a circle. Without it, if it was cut or I lost my grip, this rubber stopper would go flying across the room in basically a straight line, maybe a parabola because of gravity, depending on where it is when I lose it. But as this thing goes around, there is a force that keeps it from going in a straight line. There's a force that is constantly pulling it to be in a circle. There is an inwardly directed force, the tension of the fishing line. And any force that keeps something moving in a circle is what we call a centripetal force. Centripetal means center seeking. Really, it's pointing toward the center of the circle. So if it's over here, it's pointing this way. If it's down here, it's pointing that way. If it's over here, it's pointing up toward that. If it's there, it's pointing this way. So it's always pointed toward the center of the circle. The tension in the string is always pulling this rubber stopper towards the center of the circle.
So what is this idea of centripetal force? Well, any force causing an object to travel in a circle is called a centripetal force. So, for instance, when I'm swinging the rubber stopper around on the fishing line, tension in the string is the centripetal force. When the moon travels around the Earth, it's the Earth's gravity that provides the centripetal force. Anytime anything goes in a circle, there is a force that is causing it to go in that circle, because naturally it would just keep on moving in a straight line. Objects in motion stay in motion, right? So, in order to go in a circle, you need a force to constantly be changing that object's velocity. Now, remember, the word centripetal means center seeking. So that means that the centripetal force is always going to be pointed towards the center of the circle that it is making. For instance, if you have the Earth here and the moon out here, which way is the Earth's gravity on the moon? Well, it's always pointed toward the center of this circle. Pretend that's a circle. I didn't draw that very well. But it's always pointed toward the Earth. It's always pointed toward the center of the circle. And because of that, that's what we call a centripetal force, and it makes that object move in a circle.
So Newton's first law says objects in motion will remain in motion, and they will move in a straight line unless there's a force that acts to change that. So naturally, what will this rubber stopper do? If you give it energy, it will move in a straight line. In order to get it to move in a circle, what needs to be done is there needs to be a force acting on this to keep it from moving in a straight line and to make it change its direction. So here, you can see that the force is provided by this piece of fishing line that I have. If I were to cut this fishing line, or if I were to lose my grip, like in the first video, what would happen? This thing would go flying. And which way would it go? Well, it depends on where it is in its path. If I lost my grip right when it's at the top, it's traveling that way, which means that it would go flying across the room that way. If I lost my grip when it was here, it'd probably go straight down. If I lost my grip as it was going upward on this side, it'd probably go up towards the ceiling and come back down because of gravity. And if I lost my grip at the bottom, it'd probably go flying that way somewhere. So it depends. Where is it in its path when I lose my grip? We call that tangential velocity, the velocity that is tangent to the circle it is making.
Now it turns out that every centripetal force will follow the following equation. Fc is equal to mv squared over r. And sometimes you'll see people put a vt on this to say tangential velocity, but here's what it is. Fc is any centripetal force. M is going to be the mass of the object moving in the circle. V obviously is the velocity, the tangential velocity, how fast it's moving in that circle. And R is always going to be the radius of the circle. So for instance, let's say that I have a rubber stopper and I'm swimming this around in a circle. So here I am, we have the thing here. Here's it's like this, and it goes around. That's a terrible drawing here. Let me use a different color to make that look a little bit nicer. So it goes around in a circle, something like that. Pretend that's a circle again. And as it goes around in the circle, we measure maybe this radius is equal to half a meter, 0.5 meters. And let's say that the velocity of this thing is going at, let's make it go 2 meters per second. And let's say the mass of it is 100 grams, which is 0.1 kilograms. So I have those three variables, and I want to know what is the centripetal force. Well, in order to find that centripetal force, what am I going to do? I'm going to use the centripetal force formula. So Fc is equal to mv squared over r. That's equal to 0.1 kilograms times v is 2 meters per second squared divided by a radius of 0.5 meters. And this is equal to, when I do this, I get 0.8 newtons. So, pretty straightforward. Now you might remember Newton's second law, which said F is equal to m times a. So, if I know what a centripetal force is, I know Fc is equal to mv squared over r, I can plug these two into each other. I can take this formula and plug it into F. And I can get mv squared over r is equal to m times a, if that's the only force acting on an object. And when that happens, these masses, bam, bam, are going to cancel. This leaves us with something we call centripetal acceleration. V squared over r is equal to a, which is a centripetal acceleration, so I'm going to put a sub c there to show that this is a centripetal acceleration. Now, this is a pretty basic formula. So, for instance, in order to go around a full circle vertically, your centripetal acceleration is going to have to be more than gravity. If you don't have that kind of centripetal acceleration, you will fall off. Here's what I mean. Let's imagine a car that is going around. Have you ever seen those Hot Wheel cars, or I don't know which ones they are, Matchbox or something like that, where you have a toy car here, And you have a little launcher over here. And this thing launches the car boom, that way, and it goes around the loop, if it goes fast enough. But if it doesn't go fast enough, it gets about halfway up, and then boom, it just falls off that loop. So how fast do you have to be going in order to get around the loop? Well, I can solve that using this centripetal acceleration formula. So what do I mean by that? Here's what it is. I can move this and, okay, so how fast must the car be going in order to make it around the loop? And let's make the radius of this thing 0.25 meters. So if I know that this is the case, I can solve this thing for v. V squared over r is equal to a sub c. V squared over r is equal to a sub c. Centripetal acceleration is equal to v squared over r. I'm going to solve this for v. So I'm going to multiply by r, so it's ac times r. I'm going to square root, and that is equal to v. Now, if I want to beat gravity, well, if gravity is acting as a centripetal acceleration, that's going to be 9.81 meters per second times, what is my radius? My radius of this is 0.25 meters. 0.25 meters. That's going to give me a speed of, grab the calculator, square root of 9.81 times 0.25 will give me 1.566. So this is 1.566 meters per second. So that means if the car is going at least that fast, it will make it around the loop. But if it's not going fast enough, then it will fall off the loop. If ever you find yourself in one of these situations, the key is to go faster. The faster you go, the more likely you are to make it around that loop. So that's really all there is to it as far as centripetal force and centripetal acceleration go. Mahalo for watching, and see you next time.